Welcome to day 4, solving and graphing absolute value inequalities. So we're going to jump right into it, and we're going to solve and graph the following inequalities. All right, so we treat all these inequalities, these absolute value inequalities, the same way. First and foremost, number 1 is we make the absolute value inequality an equation. So it's going to look like this. The absolute value of 6x minus 5 equals 13. Now we're going to solve this equation like we've done many times in the past, and we're going to solve these for our critical numbers. Now, since the absolute value is already isolated, I can go ahead and say, well, 6x minus 5 equals 13, or 6x minus 5 equals the opposite of 13, or negative 13 in this case. When we go through and solve, we should get x is, add 5, that's 18, divided by 6, we get 3. Solving this next equation, we add 5 to get negative 8, divide by 6, we get x is equal to negative 4/3. So the next step is to test these regions, or regions on a number line. So these are called our critical numbers, what we just found. Okay, and we're going to take those critical numbers and we're going to plot them on a number line. And we're going to plot them in order. So negative 4/3 and then 3. And now what I do is I look at my original inequality. It's greater than or equal to. So that tells me I'm going to put a closed circle at each of these critical numbers on my number line. And what we should see is we should see 3 regions. Okay, and I'm going to choose different values from each of these regions to test. So I'm going to test when x equals negative 2, okay, when x equals 0, and when x equals 4. So I will test those, and hopefully we will see which regions are true or false. So when we plug negative 2 back into the original inequality, 6 times negative 2 is negative 12. Minus 5 is negative 17. Taking the absolute value, we get positive 17, which is in fact greater than 13. So I'm going to mark true for this region. When I test x equals 0, 6 times 0 is 0, minus 5 is negative 5. Absolute value of that is positive 5, which is not greater than 13. So this region is false. When I test x equals 4, 6 times 4 is 24, minus 5, 19. Absolute value of that is greater than 13. So we can go ahead and say it's true. So now what I do is I shade in my true regions. Okay? And the final thing we have to do is state our answer. So based off of my graph, we should be able to answer that x has to be less than or equal to negative 4/3, or, since there's a second part to my graph, x is greater than or equal to 3. I want you to try this next example that was over on the right by yourself. All right, set it equal, make it an equal or an equation, get your critical numbers, plot those critical numbers on your number line, test your regions, and then state your final answer. After you've tried it, check back and see how you did. Okay, how'd you do? So step 1, we make it an equation. Step 2, we solve that equation for our critical numbers. You should have gotten x equals 3 and x equals 19/5 for your critical numbers. Now we test our number line and we graph. So this time, because it's less than, I'm going to have open circles at my critical numbers. When I test my 3 different regions, I find that it is false on the outside regions, but true in the middle. So I shaded in between. So here is our graph, and now we have to state our answer based off of our graph. So here is our final inequality as our answer. Negative 19/5 is less than x, which is less than 3. Let's look at this next example. The only difference is now we have other stuff happening outside of our absolute value. We still follow the same steps. Step 1, make the inequality an equation. Now we know to solve absolute value equations, we must isolate our absolute value. So we need to isolate the absolute value of 2x minus 4. We do so by adding 6 to both sides and then dividing by 3. So what we should get to is the absolute value of 2x minus 4 equals 6. Now that we're isolated, we can set up our two equations, and those two equations are being 2x minus 4 equals 6 and 2x minus 4 equals negative 6. So we can solve these two equations to get our critical numbers. If we solve these, we get x equals 5 and x equals negative 1 as our critical numbers. I want you to plot these critical numbers on your number line, test your regions using the original inequality, and see what your final answer is. Check back when you're done. When I plotted my critical numbers, make sure that you have open circles there at negative 1 and 5. Make sure that they're in proper order. I found that the left region was true, my middle region was false, but my right region was also true. So my final answer was x is less than negative 1 or x is greater than 5. Try this next example on your own. Absolute value of 3x minus 1 is less than 2. You might find something odd for your final answer, and we'll discuss it afterwards. Pause the video and try it now. So, if you worked through it, you should have gotten two critical numbers, negative 1/3 and x equals 1. All right, so if you tested your regions, plotting open circles here, you should notice that you have all false regions. So our answer is no solution. Now let me tell you something. I could have looked at this original problem right from the get-go and told you that there's going to be no solutions. Can you tell me why? If we look at it, we have an absolute value of 3x minus 1 is less than a negative number. Let's take a look. If we were to plug any value in for x, pick any value, negatives, positive, or 0, after you take the absolute value of it, what do you get? You will always get a positive answer, right? So, this will always be positive. Can a positive number ever be less than a negative number? The answer is no, right? So what I could have done is I could have looked at this inequality right here, and I could say, oh, I have the absolute value, nothing is happening to that absolute value, and it is less than negative 2. That's never going to happen. So what can we conclude right away? We can jump straight to our final answer and say no solution. There's absolutely no reason we need to go through this process, okay? The number line, if you were to graph this, it would be an empty number line, just as we have here. This next example has two parts. We have absolute value of x is less than or equal to 1, or x is greater than 5. I can certainly go ahead and jump to x is greater than 5 and put that on my number line and graph that as it is, okay? To solve this portion, the inequality, the absolute value inequality, we just follow the same steps. We make it an equation and we solve for our critical numbers. In this case, we get two critical numbers, positive 1 and negative 1. And now we're going to test our regions. So, since I'm testing my regions, to the left of negative 1, I get a false statement, if we were to plug that back into our original inequality. If I plugged 0 in, I would get a true statement here. And if I plugged 2 in, I would get a false statement as well. So I'm shading in between my two critical numbers. Since this is an OR inequality, I can go ahead and state my final answer as negative 1 is less than or equal to x, which is less than or equal to 1, or x is greater than 5. The last thing we need to do is prepare for number 8 on our homework for the next time we meet. And this number 8 is actually this inequality right here. But what we can do is we can essentially treat it as two separate inequalities, okay? So we would have to go ahead and say, all right, 5 is less than x minus 3, and the absolute value of x minus 3 is less than 8. So now all we would really have to do is solve both of these inequalities, these absolute value inequalities, following the steps that we have the entire time. You will still test your regions and all of that, but the key is when you are testing your regions, you want to go back to the original inequality to see if it holds true. All right, we'll see you next time in class. If you have any questions, make sure you ask.